Good morning, everybody. Hope you all had a good first day at NEC TechTown. Today is a fair amount of opportunity to learn something about Qt. So there's this talk, and then later we have Laszlo here in the back talking about our graphics, the history and the evolution of the graphics stack, and I think we also have Andreas from Cisco talking about what they are doing. So how many Qt developers do we have in the room? Let me ask the question differently. How many developers building stuff with Qt do we have in the room? Okay, that's a fair number. Awesome. My name is Volker Hilsheimer. I have been with the Qt company now since October, after a longer hiatus. I originally was with Trolltech since 2000. I'm an R&D team lead in the Oslo team, and I'm going to talk a bit about how I have experienced, how we have over the years brought Qt to very different devices, to very different platforms, what we did on the technology side, and where we are today. Bit of a lookout perhaps also for the future. There are not going to be any variadic templates in this talk, so sorry for the C++ 17 hardcore enthusiasts. I hope there will be plenty of other opportunities for that kind of thing. So there's a bit of code, but it's hopefully not too technical for you. I'm struggling a bit with the clicker. So here is where we run Qt today, just a couple of screenshots. Top left, we see the current KDE Plasma desktop. Any KDE folks in the room? KDE users, perhaps? No? All right. Well, KDE, one of the popular Linux desktops, has been built with Qt ever since. And yeah, the current version is built with QML and Qt Quick, so very much on the bleeding edge. To the bottom left is what I think we are putting a lot of focus on in the Qt company and in the Qt project, and that is putting Qt into devices that are not mobile devices, but embedded devices. Screens in the car, medical industry, lots of interesting stuff there. So this is a car dashboard. If the light could be dimmed a bit more, I think the contrast could be a bit better. Bottom right is what I'm going to show you very briefly at the end. That is Qt running on a microcontroller unit. I have one here. And to the top right is actually Qt running as a WebAssembly. Also something I'm going to show briefly afterwards. Qt being visible like that is what perhaps led to the assumption that Qt is a widget toolkit. Of course, the widget, the visible part of Qt, the rendering, the graphics, the components, the widgets, that is what perhaps has made Qt most famous. And most valuable. And also, to be honest, from an inside perspective, it's perhaps also the hardest part of developing Qt, getting widgets, getting rendering to work on very different platforms, getting widgets look native on different platforms, getting the input management, user interface integration into desktop environments and so forth, right? There is a fair bit of work happening, of course, in the Qt project on this, but there is much more to Qt than being a widget toolkit. But it all started on a park bench in Trondheim a bunch of years ago, 25 years plus ago by now, where two guys thought, like, we need an object-oriented presentation system for the different platforms that our clients would like to work on. They were consultants for different companies and working on different crazy old commercial Unisys and Windows and so forth. They were a bit tired of having to do it all over again for every platform. So they thought, let's do a widget presentation system, and that's in a way why Qt is such a big deal. But it's of course much more than that. It's much more than just widgets, and it's much more than UI. So these are a subset of the modules that we have in Qt that do not link against Qt GUI, so they don't have any dependencies to any rendering functionality. Using those is what makes, or using Qt Core in particular, is what makes your application a Qt application. And it allows you, of course, to apply all your Qt skills that you might have. If you know how Qt works, if you know the concepts of signals and slots, the concepts of parent-child relationships and objects, if you know these basic concepts in Qt, you can apply those very effectively also to your non-graphical backend stuff in your application. All the same high-quality documentation. Lots of fairly specialized stuff here. You see like MQTT, for instance, CAN bus. Yeah, concurrency, positioning. I'm talking a bit about web channel support later. So there's tons of stuff here that is perhaps mostly interesting for certain industries, and that's also one of the things we are doing in the project these days, looking at how can we make Qt more relevant, how can we solve more of these somewhat vertical problems for specific industries. And like all good software designed, it all starts, of course, with a high-quality UML diagram. That's from 1996. That's how it all started. Actually, there is a patent number on this document to the top, and there is a 1996 of the fax, I think, to the patent office. So that's that's how it started. So much of this actually is not entirely off from how today's reality looks like. Some of the class relationships and so forth. And we ended up in 1996 with something like that. I don't know, there are some people old enough in the room to know, back in the days. So that's one of the first KDE versions here, looking all with 3D beveled buttons and the original web page. Little blast from the past. This is around the time when Qt moved from Qt 1 to Qt 2. And so let's start a bit talking about what did we do with the Qt history to make things faster, smaller, more lightweight. And one of the first things we did in the evolution of Qt was introducing copy on write value classes. So copy on write value classes are the things that you work with when you work with QString, when you work with our containers, when you work also with our higher level value types like Q network request or Q host address or Q storage info. The idea here is we want to be able to pass copies or make copies of these objects very efficiently without having to actually make a deep copy of the data, because that's a very expensive operation comparatively. It requires allocating memory. And for some of these bigger value types, we don't want that. We want to be able to pass them very quickly around, especially returning them by value, which is what you typically do. Then you don't want to make a copy of your stuff. The idea is copy on write, that once you call a method of your object that is actually not constant, so it's likely to modify the instance, then it will make a copy and have its own copy, but only then. So that is one of the first things we did in Qt, where we really looked into how can we make Qt smaller, how can we avoid allocations, how can we pass values around quicker. And so that has been around since the very early 2000s in Qt 2 that was introduced. Yeah, still part of the Qt design today. Today we have atomic reference counting underneath. So the earlier versions in the Qt 2 days, when we introduced thread support, you had to manually make sure that you make deep copies of your data when you pass a copy of a shared instance between threads. The shared instance would have race conditions. Nowadays, that's not a problem anymore. So looking a bit under the hood, how is this done? This is not exactly how it's done, but there is a public API for you to be able to use that. In Qt's classes, we do a fair amount of further optimization to allocate memory in single chunks, for instance, for QString. All the control data and the actual payload is allocated in a single chunk, for example. This is not often something you need to do for your value type. So here's an example of how you use the publicly available classes QSharedData and QSharedDataPointer. So if you want to have a payload that you are able to share via a copy on write method, then you can subclass QSharedData. That gives you the atomic reference counting implicitly, and that's where you have your data structures. You need to implement your copy operators and so forth, and then you have a public class where you use a QSharedDataPointer here to the bottom right. Hope you can see that, which is the only thing that your public interface class basically carries around. And when you make copies of the public class, you only set the depointer of the new instance to the same that you have yourself, and then the reference counting is taken care of for you behind the scenes. So that's very valuable, that's very powerful, that's something we do a lot in Qt, still using copy on write classes and implementing new copy on write classes, because it's a very elegant way for us to hide this complexity also to the API user. And it makes a fair amount of difference in terms of performance and in terms of amount of memory allocations, and then memory diffusion. Ultimately, if you run on devices where you don't have a memory management unit, for instance, you don't want to have too many mallocs. So it makes a big difference there. So yeah, like I said, thread safe reference counting since Qt 4. So you don't have to worry about that anymore, that part of passing things between the threads. There's a ton of other stuff in Qt core that is interesting. Lots of containers, lots of low-level helper functions, helper methods, like for instance, endianness conversion, if you need to do network communication, where you typically have big endian protocols, and your machine is typically these days a little endian machine, then that's useful to have. There's a very good random number generator in there that talks to your hardware unit in that respect, and very easy to use. Bunch of stuff for I/O and OS service abstraction, so file I/O, process management, and so forth. So if you want to get the most out of your Qt skills, you use these classes a lot, I hope, because that really also makes that part of your application stack platform independent. And also some of the classes we have here really don't have much of an equivalent in the standard library, like URL management, for instance, having a fully compliant URL implementation, or calendar system support. That's something we just introduced or are about to introduce in Qt 5.14. Not everybody in the world is using a Gregorian calendar, so being able to convert time zones, but also display calendar data, know how many weekdays you have. Different countries have different leap years and leap months, even in the Chinese calendar, for instance. This is the kind of stuff that is quite important, actually, if you write an internationalized application. And generally, QString is still Unicode support, since also the Qt 2 days when we moved from char star to 16-bit character arrays. So the state of affairs with Unicode support in the C++ standard is still work in progress, I believe, in the standardization group 16, where the Qt core maintainer actually is part of, Tiago Maciada. And of course, the entire object and object model is living in Qt core. So all the things that you can do with meta objects in terms of calling functions by name, parent-child relationship, event handling, event affinity of objects, and so forth, all of that is living in Qt core. And a small spike here, maybe towards the standard library. There is API, a sense of API beauty that we try to put a lot of effort on in the Qt project. So trying to make it easier cognitively to write code with QString, for instance, or with QList versus some of the standard stuff. Even though, formally it's of course a beautiful thing to have the algorithms and to soon have ranges in the standard and so forth, and you will be able to use those, of course, also with Qt. But we think that, sometimes it's nice to have a simple API to look up if there is an object in your list. All right. So as we moved forward, Qt became pretty big, and we introduced a system to make it small again. And that is a feature system that you will run into. If you look through the Qt source code, you will find that it's peppered with if-defs. If this feature is enabled, then we compile this following code. There is a high-level version of this, which is you don't want to compile all your different modules. You need to configure maybe your Qt build in a certain way. You need to maybe compile it statically versus dynamically. Maybe you don't care for threading, because that's not what your device needs. So there is the configure tool that allows you to specify how you would like to compile Qt. And then there is also the very granular ability to turn off certain parts of the code. And that is really very, very granular. So for instance, keyboard shortcut support. There is code in QLine edit that makes sure that you can copy and paste with Control-X and Control-C and Control-V or whatever you're using. That code is not being compiled in if you turn off keyboard shortcuts. And that, of course, when you are targeting an embedded device with very limited footprint, you want to be able to configure on that level. And we try to make sure that all the different combinations of features compile. Of course, they might not always. Some combinations might also not work sensibly, but generally speaking, you can go fairly much into the nitty-gritties here and take out parts of Qt. And that is something we started also in the Qt 2 days when we worked on Qt Embedded. And one of the first devices that came out with Qt Embedded, or Qt for Embedded Linux, or Qt for the embedded frame, or for the Linux frame buffer, was the Sharp Zora. So we're now around 2001. And it was a device that actually also hit the market a bit in Norway, a little bit. There was at least 5, I think, devices around. So that was one of the first things that showed us that actually we are onto something here. People would like to build devices maybe with Qt. I like the last last sentence in that paragraph. Even the choice of Java is defensible. That's when we were in 2001, and then we continued pushing that further during the Qt 3 days, and we ended up with something called the Trolltech Green Phone. So that was one of the devices that we built because we wanted to stimulate the development environment and the development community to build device software with Qt, and that's what we ended up with. And also during that process, we noticed like, okay, there is more we need to do to make Qt faster and speed things up. That was during the Q3 days in the late or middle of 2000s, and one of the things we did was what I would call PIMPL++. I guess most of you are familiar with the D pointer, the PIMPL pattern. You have a public class that you expose, and the public class carries, similar to what I just showed earlier with the shared data, a D pointer around, and the D pointer is hiding all the implementation details. It's hiding all the payload of that class, and that is in the Qt library in particular. It is because we need to maintain binary compatibility. So we want to be able to add data members to our instances, to our classes, and we can't do that if we have them in the public class because it changes the instance size, and that breaks binary compatibility. We can't do that because it would make a lot of people very unhappy, even though nobody in this room, because you don't use a KDE. But here we are. So we need to make sure, that is a slightly optimistic statement down here, that the size of an object doesn't change. It's not the size of a void star. It's at least 2 void stars because QObject has virtual functions. But the point being, we are hiding all the implementation details in the private pointer. And in that private pointer, we then have all the data members that you also saw earlier. For instance, the object knows which parent it has and so forth. And of course, you need to create that private instance at some point. We can't carry it around by value, because then we would change the public instance size. So we need to actually allocate it again explicitly using new in the constructor of QObject. And then we just access that private piece of data whenever we communicate with the object. And that's how Qt looked in the Q3 days. That's what we did there. And the problem is now, maybe you can see the problem. If we have a QObject private, and we also need a QWidget private, and we also need a QLine edit private, and there might be some more classes in between, each of those in their constructor allocate a private object. That is a lot of mallocs for the instantiation of a single object. So here, this is what it looked like in the Q3 days. You allocate a new QLine edit, you call its operator new basically, that malloc stuff. QLine edit constructor calls the QWidget constructor, calls the QObject constructor, and then you create these private instances. So that's 4 mallocs for a single instance of a type. That's not great. Again, mallocs are expensive operations, especially on devices with low memory, first of all, but also no memory management unit. So we want to get rid of this. We want to make this something else, and that's what we ended up with. Basically, we say, well, can we somehow, and we can, make the QObject private and QWidget private and QLine edit private instances inherit each other, so that we allocate only one of them, the one at the leaf, and then it implicitly creates all the other stuff. So that's what we have now in Qt4 and Qt5. Qt5 being the 5.13, this current version. So we basically, what you will see in Qt is that we have these protected constructors that we are using to pass the instance of the private object basically up the class hierarchy. So QLine edit still mallocs versus operator new, QLine edit private, and sends it then through the QWidget private protected constructor, and then through the QObject private protected constructor. And the QObject protected constructor is the only one that has then a D pointer. So that's also another benefit. We don't have every public class carry its own D pointer, which is basically the same thing. So that's making the public class instances smaller. It's reducing the number of mallocs quite a bit. Not a rocket science, but a nice little thing that we did in Qt4. The challenge here is, of course, that we now have a cross-module private dependencies. So these private classes need to be defined in headers that we can actually expose to subclasses, and that is one of the challenges that we have now sometimes and now and again, that we have cross-module private API dependencies that sometimes break things in unexpected ways or break the compilation if nothing else. But that's really a matter of managing these dependencies. Okay, so now we are in 2006, and the green phone is there, and it's all right. it's all right enough for Nokia to like what we are doing, and so Nokia is acquiring Trolltech. And what Nokia says is like, hey, you guys build a phone. We also want to build a phone with Qt. The phone that we would like to build looks maybe a bit different. It's maybe having slightly different expectations and requirements. So the question was like, how do we get from this green phone, which was a developer device, which was suffering visibly from some of the designs that we still had in Q3 and Q4? How do we get from there to something that is really different in the sense of user experience, responsiveness, touch, friendliness, dynamic, fluid user interfaces? Does anybody know what this is? That's a memory and hardware debugger and profiler. It's a Lauterbach device, so that's the kind of device that Nokia could afford and Trolltech could never have afforded. So that's a very cool piece of hardware that allowed us really to see what is the CPU doing, when is the CPU in which state during execution of our code. So as we learned what it actually means to build software for these embedded devices for real, coming out of the application development background, coming out of the KDE world, starting to build devices with Qt. This was quite a watershed moment, I think, for our R&D organization to really learn about that stuff. And that helped us ultimately to understand what we need to do. And one of the things we learned was, if you want to have 60 frames per second, then we can't continue to build our user interfaces using imperative development paradigms. I'm on record as a support engineer back in the Trolltech days to tell people you don't need 60 frames per second. The human eye can only resolve 24 frames per second. That's what we learned in biology class. Not true. If you have like TFT displays and computer-generated content, you want to have 60 frames per second. That's what your brain can resolve, and that's what gives you this idea of this is actually a fluid animation. But yeah, ultimately we needed to go there, and to go there we needed to have another way of expressing user interfaces than having a list of imperative statements doing that, because that is not giving the hardware acceleration infrastructure the data structures that they need to be able to actually optimally render your stuff. OpenGL works on a scene graph. Many other, or all of the other hardware acceleration rendering frameworks today work on a scene graph. They don't work with a list of statements. So we need to do something there, and another insight was designer-developer cooperation actually matters, and for that C and C++ as an expression language is not optimal. Let's put it like that. Designers looking at C++ code, they will probably not look at your C++ code. We want to be able, and that's one of the things that Nokia really tried to achieve, we want to be able to have designers and developers sit together, and that's something we're still working on today, and working on a code base that is meaningful for both sides, so that they can work on the same asset. Versus designer does his Photoshop, throws it over to the developer tries to do something that is like, yeah, this looks a bit like that Photoshop thing, it's the best I can do with the tools I have, but actually it's not quite what the designer had in mind. Maybe some of you have experienced this. So that's where declarative UI and QML enters the scene, around the 2010, 2011 timeframe. Laszlo is probably going to talk a bit more about that later, so I'm not spending a lot of time on this, but I would like to demo something quickly. That's the kind of thing you would build with QML. So that's a very simple example. I'm not sure if you can see this with the light being somewhat on the bright side. So this is, for instance, how you would express. This is a clock example. Maybe I run this first so that you know what I'm talking about. No, not this one. Here we go. So that's a simple clock example. That's the kind of thing that you can very easily do with QML. There are some details here that are very nice. First of all, if you see how the second pointer moves, it moves with an easing curve, right? It's not a snap move to the next position. It actually bounces even a little bit, right? So that's the kind of stuff that designers want. And if you have that somewhere in your Photoshop file, the developer might not see it, but implementing that in QML is really simple. So here you have different PNG files, which is typically the artifacts that designers work with, bitmaps and PNGs, to make the different assets work, especially for fixed size displays. You don't need to worry about scalability that much. You know how big your resolution will be, and then you can very simply express the structure of your clock in this case. You have a background picture, that is the clock, and then you have your second rotation here, for instance. I think, and here we have the spring animation, and that makes it bounce a little. So that's the kind of expressiveness that we wanted to have in Qt's UI machinery, so that people can write these kind of things that you want to have on your mobile devices. All right, let's continue. All right, so by 2011 then we had actually a Nokia device on the market that was a very cool device. Sadly, it was the only device that Nokia built with embedded Linux and with Qt. But here we are, the N9. I had one, I loved it, but sadly, bit too late. The story is known. But nevertheless, the small number of very cool devices that we had built with Qt. So there are a couple of other things that we learned from this process. One of them was that porting Qt to different platforms was bloody hard. And we had to do that in the Nokia days. We had the S60 Symbian platform. We had different Linux backends and rendering stacks and so forth that we needed to work with. We had Wayland starting to emerge as a composition engine. So we needed to make it easier for us coming out of the Nokia experience. How can we do this easier? Maintaining the existing ports that we had was messy. There was a lot of entanglement, and there still is a fair amount of if dev Windows, then do this in the higher level classes, but we have reduced this quite a bit. It made maintaining the code very fragile. So in order to be able to reach new platforms and maintain code more effectively, we needed to have a better abstraction. So we needed something new, and that's basically one of the first things that we did for Qt 5. From an architectural point of view, and that was to introduce Qt's platform abstraction, which gives us a slightly leaky abstraction and not a complete abstraction, but a fairly decent abstraction for having very different aspects of platform integration implemented in different parts of code that don't know about each other. So Windows system integration, for instance, making sure that your window stays on top and these kind of things, maximizing, minimizing the things that you care about if you're writing applications for the desktop. Screen and DPI awareness, how many displays do you have? Are they high DPI or not? Very platform dependent. Rendering engines, of course, different backends for OpenGL, different backends for now in the future. Yeah, Laszlo will talk about that more, different rendering backends. Surface management in that respect as well, our OpenGL textures and so forth. And then input handling, theme integration. So on the desktop, you want to have a system tray icon thing for your application perhaps, or you want to follow the theme of the user, the color scheme and so forth, the fonts. So that all that stuff is now hidden behind interfaces designed for that purpose. And that has led to a fairly good proliferation of different desktops and embedded platform support in Qt. Much of which is actually contributed and maintained by community members. So, the Qt is an open source project. I didn't say that explicitly, but here we are. So lots of that stuff is actually contributed to by community members. So we have the desktop platforms, of course, where still lots of the work is happening on that level. macOS, infamous for changing things fairly rapidly between different versions. 5.15 comes out, Catalina, with a completely different new notification API backend, for instance. So much of the plumbing much of the work that we spent on the desktop maintenance is done on that level with the plumbing. Same with Windows. Then we have mobile platform support. That was originally developed actually by the community, the Necessitas project, to bring Qt to Android. iOS is of course, something we do. And then we have the different frame buffers, e.g. LFS, and then also for people that need runtime, real-time guarantees, QNX integrity, and WebGL. Okay, Qt and WebGL. And that is actually pretty cool. That's something I would like to show. Qt in the browser. All right, let's end the show because otherwise you don't see anything. So we just saw that clocks example running as a regular native application on my Mac. I can run that as a WebGL server. The only thing I'm doing here is I change the command used to execute or to run the executable. That's the only thing happening in the background, and basically we just say use the platform plugin for WebGL. So if I run that now, yeah, I will get asked by my Mac to actually allow that it starts listening to a socket, and that's it. Now I have it running. Down there, here we are. And now I want to run the browser. Here we are. So that's your Qt QML app streaming its UI over a WebSocket in WebGL to a browser that's basically connecting to localhost 8080 here. Exactly the same code. Not a line of code changed. I can interact with it. So that's pretty cool, and that's something that we see a lot of customers being very interested in. If you build an embedded device, for instance, that is headless, because you don't want to have to cash out for a TFT display for every one of your devices in your factory or whatever, but you would rather have your operator walk up to that device with an iPad to maintain it or to operate it, you can expose that device's user interface over a WebGL stream, and then all you have to do is connect to it. There are some limitations still there. There is, for instance, only one user is allowed to connect to it. There is no session handling in Qt. Qt is not a web framework with hundreds of users talking to some multi-tier architecture. So it's limited in that respect. Also, there is currently no security model. Anybody can connect now to this server. So we need to have some sort of authentication, and of course, you could implement this in your application, but it's perhaps something you would like the framework to do. But nevertheless, it's a good start. So if you are interested in this kind of stuff, let me know. We can talk about it. All right. Let's kill that server. So I mentioned WebSockets, but there's of course much more to it. Qt has a fairly rich library for network communication. Of course, your standard TCP, UDP stuff. One of the nice things here is that we handle a lot of the stuff that's behind the scenes transparently for you. Like for instance, I mentioned Endian earlier today. That is something where Qt gives you the tools to have your network communication code, not have to worry about platform details. A fair amount of serialization support, so different stacks for, well, JSON is, that's what you use to communicate with, sort of consume some web services. But CBOR, for instance, that's a concise binary object representation, very similar to JSON in what it does, but it's a binary format, so much more compressed, much less bandwidth consuming. There we have stream and DOM support. XML, of course, and then we have, if you don't care for interoperability, you have Qt's data stream, which you can just use to send data over the wire. Qt makes it very easy to support IPv6, so we have support for IPv6 and internationalized domain names. And from a security perspective, we do have support in Qt for SSL sockets, for QTTLS. So make sure that you have encrypted communication, unless you really just talk on the local host. Should be a best practice these days, or a code smell almost to not do that. So a lot of stuff happening in the network stack has been around for many years, continues to be developed. Also now talking, for instance, to secure channel and to S channel, or secure transport and S channel, I should say, in addition to OpenSSL, and also moving with the times. TLS 1.3 these days is supported in the Qt network stack. in order to get the WebGL support done, we needed to have something a bit more. And one of those was, well, we actually need to run an HTTP server. And that is a project that's currently in the Qt Labs. You might find Michael Svetkin running around here at the conference from Cisco. He is actually contributing to that. So the idea is we want to make it very easy for people to expose parts of their Qt application as a web service using an HTTP server API that is very much inspired by what you have, for instance, in the Python world with the Flask framework. So making it very easy to connect existing Qt C++ APIs to an HTTP endpoint. So this would be the simple hello world example, which is really like 30 lines of code. That's pretty cool. So that's currently being worked on. If you would like to try it out, we would be very happy for your feedback, and we also would like to hear, where do you find this useful? We have customers that have devices in like building controls, where they would like to be able to access data, measure points, and so forth over an HTTP endpoint, being able to not have to run your Nginx server or whatever, or something else heavyweight on that device, but rather have it completely baked into your application is something that's very attractive for them. For diagnostics of devices, this could be very useful. You can really introspect data within the device. Of course, security, always a thing in that context, but that's really nothing specific to our particular HTTP server. So that's one of the things we had to develop anyway for the WebGL support. So, here we are, having it as a public API. And then I mentioned WebSockets. WebSockets are a protocol that is addressing a number of shortcomings of HTTP in terms of bidirectional communication, latency, handshake overhead, and so forth. So this is from the official website regarding RFC 6455. Yeah, the previous thing has required something in open abuse with polling and so forth if you want to have real bidirectional communication. So with WebSockets, you have a lot of advantages in that it is actually designed for bidirectional communication, so you can actually have a meaningful interaction between client and server. You have a very high latency communication stack where there is very little overhead, and it's also, well, it talks over an HTTP protocol, so it actually passes very easily through proxies and firewalls. And then in addition, we have Web Channel. So Qt Web Channel is a module that allows you then to expose a C++ QObject API to a web application, to JavaScript, for instance. So you can very easily have a browser implementing a UI that ultimately talks to your C++ Qt code. Let's have a look. So here we have, let me just make that the active project, a chat server, which basically has a very standard Qt API with properties. It's a chat server that basically maintains a list of users and echoes messages back to all users except the one that sent it. So it's not exactly rocket science, but it's just looking at, well, you have a standard C++ API here where you mark your methods as invocable. That's a standard way in Qt to make it possible for you to call methods by name. If you have the string of the method that you want to call from your scripting language or from your scripting binding, with a Qt meta object system, you can then call that method. And yeah, that's basically it. That's all you have to do in order to do that. And then you need to put a bit of plumbing into place in order to expose that object, that class, as a web channel API. So we have a WebSocket here. So that happens over WebSocket. Web channel happens over WebSocket. You have a WebSocket server at the top, and then you wrap your you have a wrapper that basically takes care of instantiating new objects whenever there is a new client connecting. So that you have on the server side, you have an object that represents each connection, and then you expose that over a channel here, and just run your event loop. So if I run that example, let's see. Okay, now I'm running here in a terminal. I'm running that server, and if I now start the browser side of this, which is basically just, again, connecting to 8080. Here we are, done. So this is coming from the C++ side. I logged in, and here is my JavaScript side. So we actually have a JavaScript library in Qt that takes care of all the plumbing between your web application. Your website needs to talk to a web channel backend. All right, so if you know Qt, again, you can very easily build a backend for a web application, which is pretty cool. All right. Whee. Okay. Where were we? And then while we are in the web, Qt for WebAssembly is a platform that we have today as well, fully supported in the limitations of what WebAssembly can do. WebAssembly is a bytecode format, if you want, that you can use to compile your C++ code into, and then browsers that support WebAssembly will execute that bytecode in a sandboxed environment. So it allows you to distribute your Qt application as with a zero deploy solution basically for your Qt application. As long as you like your users to run your Qt application in a browser with the limitations that we have there. For instance, thread support is still not entirely awesome, and the storage, the persistent storage in WebAssembly is still a bit of a shaky bit. Let's have a quick look at that as well. So if I now run the clocks example again, and this time I run it as a WebAssembly, I'm having a virtual machine running on my Mac here that basically runs Nginx and has the WebAssembly pre-compiled. If we do this here, it's taking 5 minutes or so just to link. That's because the toolchain is pretty significant. So let's not do that, but let's just maybe run it. So you see here now, Safari comes up with a web page that points to my local VM, where the clocks example is built. And now you see that Safari is compiling that bytecode into the code that's natively running on a Mac. And here we are. Okay, so same code, exactly the same code. Not a single line has changed. I just compiled that code into a WebAssembly. And can now distribute this to any of you on any platform with any browser, which is pretty cool. All right. And then last but not least, or latest and smallest but not least, I should say, is Qt for microcontroller units. So that's something we have been spending quite a bit of time on over the last year, or 1.5 years perhaps. Different strategies that we tried out. There is one that is trying to make Qt. We have the feature system, we have the platform integration, abstraction, using these mechanisms to make the Qt, the proper Qt, smaller, so that it can fit onto a microcontroller unit, sitting on top of microcontroller real-time operating systems like RTMS, for instance, is what we spent time on in the beginning. That's something we showcased at Embedded World in Nuremberg earlier this year in February. There you can basically use your Qt QML application and build it into a binary that runs on these devices. It's still a fairly significant memory footprint. You talk about like 10-ish megabytes, which is a bit beyond the comfort level for people that build stuff with microcontrollers, because you need external memory, and that is not something you often want. So it's one option. We build Qt down into a very small set of the features that you need, but then you have basically the entire Qt stack at your disposal, depending on how much footprint you have. And seeing that this is still a little bit too big for many of the people that would like to use their Qt skills and their QML skills to target entirely new device domains. For example, home appliances. A fridge. Smart fridges are a thing, apparently, where you have a nice display that you can use to operate your fridge. If you have too much memory needed for that display to work, your power footprint goes to the point where you are no longer AAA. And that makes your fridge a lot less valuable than if you are in that AAA energy profile segment. So these are the kind of things that we learned while we validated the idea of what would it take to bring Qt to the microcontroller units. And yeah, smaller is better is the general statement that we got there. So what we have done now is basically develop a dedicated rendering engine for QML for microcontrollers. There is not a lot of other Qt underneath. There is the QML language. So if you are familiar with QML, if your designers are familiar with QML, you can develop your user interfaces more or less as before. Not all of the features and bells and whistles are part of it yet, but we'll get there. But once you have a team in your house that knows how to develop these user interfaces using QML, then you can now also build software for devices that have that kind of footprint. So of course we need 3 megabytes for a frame buffer. If you have 3 megapixels, then yeah, you need 3 megabytes. But the SRAM number here is the interesting one. We are like 226 kilobytes. Should be enough for everybody. Or 640, right. So being able to run actually a Qt UI, a QML UI, like well below 1 megabyte of RAM is pretty cool. I have this device here. That's a STMicro32F7. Let's see if it works, or if I broke it. There will be 2 red lights coming on here. One of them once the device, the carrier board gets power, and then the other one when the actual machine gets execution starts. Before that second line turns on, there is no code executed. So if you want to pay attention to how long it takes. That was hopefully pretty fast. I didn't see anything, but something in the like millisecond area. Of course, handling it, holding it the right way upside down is helps. So here we have that at our stand outside as well. So that's exactly what you are seeing here, just different software, different reference example. It's interactable. It's a touchscreen support, and this is QML developed user interface, 60 frames per second with SRAM usage well below a megabyte. So that's something we announced a couple of days ago, I think, end of August perhaps. Looking forward to your feedback here. So again, the idea is you are having people in your team, or you are somebody who develops software with Qt and with QML. You are familiar with the stack, you are familiar with the tools and the concepts, and you are now having basically a completely different way to employ your skills and your experience for something that otherwise you would have to learn a very different set of tools and a very different set of frameworks. So that's the idea. So yeah, if you have questions about this, please meet us outside. That's where I will be after this talk. So visit our stand, get a T-shirt. We are hiring C++ developers, product managers, people that like to do this kind of stuff. Yeah, thank you very much. That was what I had to talk about in terms of how we brought Qt over the years to different platforms, different devices, hopefully making you a more valuable professional, because if you know Qt, now you can basically work on almost anything. So yeah, thank you very much. If you have questions, I'm here.